Welcome to Data Mining Lesson video on extensions of the linear model. We've been talking about linear regression, and in this video we're going to talk about ways to do regression, relax the requirements that the relationship between inputs and outputs is linear. We've talked about a method previously where nonlinear regression can be performed using k-nearest neighbors. So what we're going to talk about in this lesson is a parametric method for regression that relaxes the linear requirements. It's not going to be as nonlinear flexible as k-nearest neighbors. It's going to be somewhere between that and linear regression. And so there's a couple of ways we can relax the linear requirements. The first method is to do nonlinear regression and have it nonlinear with respect to a single input variable, as in the formula shown here. And you'll notice this term here, there's a beta times one of our variables x, and x is squared, and then we could have additional terms as well. And so this is one way to relax the linear requirement, having some of our terms that are squared or cubed. We would have a polynomial function of each of our input variables instead of a linear function. Another way we can relax the linear requirements is to have our functional form not additive with respect to the inputs. And so you'll notice in this formula here, there's a beta 3 times the product of x1 and x2. And so this is what we think of as an interaction term. So x1 and x2 are different variables, but they're interacting in some way. So we are not doing regression on them separately and then adding the results together. They're interacting with each other. Let's walk through some examples with these two different ways of relaxing the linear requirements. And first, we're going to do sales using our advertising data. We talked in our previous lesson video. We're going to do regression with sales as a function of television advertising and radio advertising, and then a new term, which is going to be radio advertising times television. And so when we do regression using the formula shown here, and this last term is the one that's making it nonlinear, we have this as a result. So you'll notice we have our three different variables, TV, radio, and TV times radio. And significantly, the t statistic for the TV times radio is quite large in comparison to the t statistic for the other variables. And the p-value tells us that this new independent variable that we've created, TV times radio, is significant. Now, you want to be careful about interpreting this. It may be possibly that in markets where people are advertising TV and radio, they have an effect where advertising in both hits more consumers and increases sales significantly, or it could just be in markets where there's a large sales, companies have enough money left over to advertise in both TV and radio. And so it's very important to not infer cause and effect, but we can infer that the TV times radio is significant in this situation. But the relationship has a significant improvement when we include this nonlinear interaction term. And the other method we talked about for creating a nonlinear regression is to take one of our variables and take that variable raised to some exponent. And so in this example, we're going to estimate miles per gallon. And we're going to do that as a function of horsepower, and we're going to use this quadratic equation for horsepower. Right? So it's the constant term plus a linear term, and then plus this quadratic term. And so when we do this regression, we get the table here. And you'll notice that the t statistic for horsepower squared and the p-value tell us that this horsepower squared term is significant. And on the plot on the right-hand side, you'll notice that the linear regression, shown in gold, gives us a decent fit, some measure of trend. But when you look at the blue, let's get a light blue to point to it. That curve corresponds to the degree 2 polynomial, which we've shown in the regression on the left-hand side of that table, and that seems to give us a better fit to this data than just to the linear regression. Also shown as a degree 5, questionable. Maybe the degree 5 adds improvement, maybe it doesn't. Something you'll often notice when you take higher degree polynomial regressions, things like this tail that I'm circling in red on the plot, doesn't seem to represent any data, but out at the extremes, when you do high polynomials, you tend to get estimates that seem unreasonable based on the data. So in review and what we've talked about doing nonlinear regression. And this is a regression that we're setting up in parametric equations similar to linear regression, but we're relaxing that linear requirement. And so the two ways we talked about doing that is using regression where the formula is non-additive with respect to the multiple inputs, meaning there's interaction terms, or where the regression is nonlinear with respect to an individual input, meaning there's polynomial functions of individual inputs. Thank you very much.